Hey, this is OXDF, and today we're looking at the FlareOn 2022 challenge, specifically challenge number 6, a la mode. Let's go ahead and jump in. We've got, what they've given us is a supposedly .NET binary. So we're going to open it up in DNSpy, and this font is kind of tiny. We're not going to be here very long, so don't worry about, well, I guess apologies for the small font, but basically we've got this one FlareOn, I think that's a namespace, and then there's a flag class with two functions. We can look at the flag function, it's just empty. And then there's the get flag function, which takes a password, and it is going to encode that password, connect to a named pipe named FlareOn, and then it's going to write the password in, and then it's going to read back something into a string and return that string. So there's not a lot going on here, like not much I can do with that. Like that name pipe doesn't exist by default on Windows. Obviously, something has to start it, something has to be serving that, or sending the flag into that pipe, checking the password presumably. So clearly there's something more going on here than what we've got. I almost never recommend opening up .NET binaries in Ghidra, but with nothing else, looking for something else, let's do that. And we'll see, this is a DLL. And so it's got this kind of these two exports, which is normally you'd expect to have more, at least one additional export. But, entry is sort of entry, and it doesn't have, if we look here, it basically calls core DllMain, and core DllMain doesn't exist here. It's an external reference. So there's not much we can do with that. Now, interestingly, I probably should have shown this at the beginning. We did get a text file along with this one that says, hey, IR team, it looks like the sample has some other binary it might interact with. Do you have any other files that might help? And they said, nope, sorry, this is all we got from the client. Let us know what you got. So it's like a good hint that we got to find that other interaction somewhere, right? So let's jump over to this DllMain. This is a standard, I got for Microsoft convention here, and I'll pull up the file for it, or the documentation for it. And basically it typically looks like this. It takes in the instance of the handle to the DLL that's being loaded. So this step back. This is run whenever a process or thread starts or exits. It runs this for each DLL that is loaded. So when a DLL gets loaded, its DllMain gets run. And so it's a way it can do pre-processing or any kind of setting up or initialization it needs to do. And so it typically takes in a handle to the DLL as well as a reason, and then this last argument's reserved. And so then they say, okay, let's switch on the reason, and if it's attached, do this. If it's a thread attached, do this. Detached, blah blah blah. Right? So now that's how you can do it. We can jump over and see that we have, basically the same structure here. We have this instance. It's a long versus I forget what it was in the other one, but it's a value of some kind. This is null. But instead of doing all that switching and stuff, basically just if parameter 2, the reason equals 1, and we can set an equate here and do DLL and find, let's see if DLL process attach. So we can, if it's process attach, initialize a security cookie. I'm not going to go too deep, it's just basically setting a bunch of globals. We could come back to that, but let's for now keep going. And then it's going to call DllMain dispatch, and this looks a lot like what I saw there on the Microsoft page, right? So we're doing a bunch of checking based on param2 and doing certain stuff based on it, right? So we'll see, and we can go through here and set equates for all of these. We know these constants all start with DLL underscore, so we can just use that. So it's not attach, set equate, DLL, thread attach. So, if it's not blah, blah, blah. I took we could go through and figure out all the logic of this, but what I actually just saw first right off the bat is basically there's only one other function that gets called, right? There's these kind of other things that look kind of boilerplatey, but then there's this function 1163. All the functions start 1000, so I'm just going to refer to their last four. So 1163. So it gets called one way or another. Let's see what that does. Very simple. It takes in, param2 has to be 1. Okay, param1 doesn't even seem to be used, at least not obviously. So there's a function call, and then there's a global that presumably is going to have an address of a function that gets called again with this. We'll take a look at the first one. So we can look at this, and then we start off right here with 3 just setting function variables into these. And what I'll do with these globals, I can go and look at these functions and figure out what they do, but just to start off right away, I can rename these globals things like fun, 14, 26, just like that, right? And so now we can rename this one FUN 1451. And what this, the reason I go through and do this is now when I'm jumping around somewhere else and 1493, in fact, we can go back and see if any of those globals, because I don't remember the globals off the top of my head, right? If any of those globals was this one right here, 5A30, now they would be renamed to do that. And I would know, oh, I should go look at this other, I know what it's going to be, so I can go look at it, right? Though that didn't help me there, though. So the next I have this call to 12 dB. I'm going to want to look at that. And then I have all these pairs. Each pair of lines calls 14AE, takes the result and returns it, and then uses both these results with 12.5C. And it does that over and over again, setting a bunch of globals, and it returns. So we need to know what this one does. So we'll jump over here. And this right here is kind of, this is a place where the decompile is actually kind of confusing, and the disassembly is actually clearer, to me at least. What we're going to do is we're going to go into the FS register and get the offset of 30. I got all the documentation for where this is, but in my blog post, if you want to check that out, link in the description. But this is going into the process environment block, the PEB. And then basically by going to C and then 14, we're getting the linked list of loaded DLLs by the EXE. So we're getting all the loaded DLLs in, I believe this is in memory order. The top of that list is going to be the pointer to the next object in the list. So we're going to start get the first, second, third object. And then we're going to go 10 bytes into that and get that's actually the pointer to the function, where the function is in memory, or not the function, the DLL in memory is exactly. So this is the point where I can get that all with research. Alternatively, we could switch over to X32 debug and open up, let's see, how does this work.dll, and step in. Now, I want to show you, this is kind of cool. I didn't really appreciate this. In the past, years ago, I would have gone in and I would have debugged run DLL32, and I would have set the command line to open this, and then I would have tried to like catch on module loads with a breakpoint and find the right breakpoint and blah, blah, blah. It must have updated, or maybe this was always there, I just didn't know it, X32 debug. But basically now, what it did when I open up a DLL like that is, let's see, let's minimize all this stuff. We can see, because I'm working off the desktop here, you can see in addition to, in the same folder, in this case the desktop, as that DLL, it makes a DLL loader 32 with some random stuff, and it then runs that binary, which loads your DLL and gives you a breakpoint when you get to that DLL entry, which is actually really nice. So you can see here where this is the entry point for the DLL. If I refresh this, you'll see the DLL, this number changes. So here's 17E4, 2AEFE. So basically every time, as soon as you finish execution, it deletes this binary, and then restarting it, another one comes. So, so let's go ahead, let's go back here. And this is really how I like to do dynamic analysis, is to bounce back and forth. Let's go right here to this function call right here, which is at 1311. And we'll come over here to Control G, 1, 1, 2, 3, 1311. I thought it was at 1311. Oh, let's see, this was cancel. We got to run to at least load the, now we got to get the binary in memory. So we'll come down here, 1311, and we will put a breakpoint there with F2, and we will run to that. We hit the breakpoint. We can see, I don't believe this thing takes any arguments, and if we step, we get this 766C000, but most interestingly, you can see it starts with MZ. If we view this in the dump, we see this is actually a loaded DLL. If we jump over the memory map, we can see, right, it actually highlights it for us because we're on it. That's kernelbase.dll. So what we've done is we found in memory kernelbase.dll. We can tell right away. At this point, we know this binary doesn't want to show what functions it does. You know, common technique for malware analysis is to open this up and say, oh, let's look at the imports and see what it's doing. And if we look through here, we won't see, I don't think, any references to name pipe, right? Let's see. So this thing's clearly not creating name pipes, right? Well, if it wants to, it's not doing that using the standard way of loading libraries and then referencing their functions. But there's nothing to stop it from finding the address of kernel base itself and then finding functions within it. So I already feel pretty comfortable that's what it's going to do. But let's keep stepping through. So jump back here into X32, and we can keep going through a little bit here. So we know that if we go to Ghidra, we know this right here. Let's see. Back. make this over here. So we know ivar1 is kernelbase.dll address. And that is what's being passed into this other function multiple times. So now we need to figure out what this next 14AE does. And let's just do the same thing here, where if we come over here and we step through, now this is taking in two variables, or two arguments. The first one, following the dump, is this kind of jumbled up string here. We can see it's about 12 long. And the second function, or function argument, is a null buffer. So let's again, we could dive into this and look at it, but let's just step over it and see what happens. Cool, our return is close handle. So, and that is still filling these 12 bytes. And in fact, the buffer, both the returned buffer, not the return buffer, the passed in buffer, the argument that was empty, now holds close handle, and the return is close handle. So we can go over here, and what I would do is something like, I'm going to rename this global to close handle encrypted or something like that. And this will be, if we, we can center click on this and see it's the same buffer being passed in over and over again. So we're going to rename this like I don't know if it's crypt or code, but we're just going to call it crypt. We'll be lazy here and call it decrypt buffer. Cool. Okay, so let's go back over here, and if we step a few more, we can see we're now at the second function, and this is the function that's now going to take in kernel DLL address or kernel base address and the string, and it returns nothing. I really expected it to return that, and then I realized like close handle, I don't even think that's part of kernel base. I think that's, you see that's actually imported here with kernel DLL, the kernel 32 DLL. So it kind of makes sense that it didn't find anything. We could come over here and say, oops, how did I get here? Let's go back. We now know this global though is going to be close handle, and we'll call it fail because it didn't actually manage to get close handle. And so we can now step through, if we step through and do this again, so now we have, we're back to the string decode one. And so that's another string. And this, interestingly, it's actually the buffer now that we're passing in still has close handle in it. So I think it's actually using, these have to be done in order, and it's using the previous decoded string to encode the next one. So it's important to keep track of this buffer as we go through. So if we step over this, we see now we get back connect name pipe. In fact, the buffer has been updated. We step through, we're now passing connect name pipe in with kernel DLL, kernel base, and now we actually do get the address of that function. We can, if we right click here and do following disassembler, we can see this is connect name pipe. I'll just get EIP back. So we can come over here and we can label, rename global, and we'll just call this one named pipe, something like that. And now we've got that. I'm going to pause the video here and go ahead and do the rest of these because I don't think watching me do 10 of these is going to be super fun. But I think it's important because we're going to come across these as we come across these later in the binary. Again, this global, seeing global blah 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 or data blah 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 doesn't really mean anything to me. But if I can see, oh, that's connect name pipe, it's going to be useful. So we'll go ahead and knock that out right now. Okay, so we've got all of these labeled. We didn't dive into these functions, but we can when we at least change the globals so that if we run into them, we can come back to them. We can rename this function to get kernel base ADDR. We can rename this function to decrypt string, and we can rename this function to, oops, not edit signature. Let's edit the name to get function ADDR, and I know I'm going back and forth between camel case and underscores, but we'll deal with it for now. So this is all looking good. We kind of have an idea what this one does. In fact, we can even say rename function. This will be like init global function funcs. There we go. We'll go with that. Awesome. So we've got this now. Let's step back up here. See if we can find where. So here we have our init global funcs, and now even right there, we've already solved it. We are now going to create a thread using that loaded create thread, and that's going to be based off of 1094. So let's jump over to function 1094. This is going to be the thread that gets created, and this is actually not pretty clear what's happening. We can look through. So the first thing we're going to do is we're going to decrypt a string here to this. Now we can pull up the description for create name pipe, but this is going to be the pipe name. We can call this like, well, I guess we can't actually, we have to call this like res or something because it's used all different places. It gets reset a bunch of times, but this is going to be the pipe name. So we can have a decrypt string. Now we renamed that global in the previous one, which means this is actually a new global buffer here. So we might be able to get to it. You know, it may have been used somewhere else, but if it just jumps straight to this thread and it hasn't, it's possible this is all nulls again or in its default value, and we can actually debug this. So we're going to create a name pipe. We're going to connect to the name pipe. We're going to read from that name pipe. We're going to then, let's see, local 50. The thing we read file, this is the output buffer for that, is going to get passed into fung 1000, 1000, and then we're going to write something back to it. So that sounds pretty promising. Like we found our name pipe server. We can, let's see if we can debug this though. So to do that, what we're going to do is we are going to just cheat a lot. And we're going to come over here right now and we're going to say modify value. We'll do 1, 2, 3. We have now moved, we've now just jumped to that function. Now, this is going to, I don't know if it's going to work or not. Let's see. I don't know if I've tried this. We can start stepping through this here. So I think this is going to be, we're getting heap. Actually, to do this, now I would presumably create the name pipe and stand up and listen for that. And I don't actually want to debug that. I'm changing my mind here as we go. What I want to do is I want to see what happens to, so we were going to read, and we think we're going to read the password because that's what we saw in the .NET code. And that's going to get passed in here. So like, let's see, this is, presumably we're going to call this password, ? And we've got our local C here. Why is it not, oh, there we go. And it's not initialized anywhere else. So I think, in the way it's being passed as a pointer, this function is going to write something to local C, then it's going to come out as the file here. So let's check this out. And if we look here, we can see, yeah, local2 is just set. In fact, it's just set either to one of these two values. And then it's going, so look, what all that matters coming in here is the password. So that, oh, I think I actually did this by accident. That's actually what I want to do. I want to actually come to this function. I want to debug from here because, yeah, the password won't be set right. But like if I come here and say, actually, this is where I did jump. Let's do that again. Modify value. We jump here, and now we're at the password function. And so we expect that this is a password. In fact, we could make this the password. Let's see, what is this address right here? 1001 5000. So let's see if we can change. One is it? This right here. Let's edit this value. Binary edit, and we will make this 00500110. So in reverse order, that's 1001 5000. And if we do that, now this first argument points to, oops, that's not what I was hoping it was going to point to. Huh, what was it before? I must have put the wrong address in there. Let's find a string of some kind. So this will be, I guess we'll do this first random one here. So 5070. So we'll binary edit 70. And now if we follow that in the dump, we've got a pointer to a string. Okay. I don't think this really matters, but tangent, we'll go for it. So if we start stepping through here, let's go back here and look at what's going on in this function. It is going to take in this, it's going to do something here that we completely don't, it's going to do something. It's going to take a global and a local 40C. Then this next one's going to take a different global and local 40C. And then we're going to compare this resulting global. So we're going to, we can just right there, it's going to compare that to our password and using a long string compare. And so pretty quickly I can say, is this, decrypted password like that? And param1 we believe is rename variable input password. Now we know that we have that compare. We could spend some time trying to look at this. In fact, I'll show in the blog post that this is actually RC4, just like the previous one, where we're doing the key scheduling algorithm and the pseudo-random generation stream / encryption decryption. But we don't need to. We're going to debug. So let's go through here, and we'll step over. So this is, I believe, the key generation, the decryption, and the string compare. And you can see right over here that we are comparing my voice in nice and neat with the string I passed in. Right, so cool. We've got a password. I'm not sure what password's going to do for us, but we've got one. So let's go here now. We can keep going. Let's see, I don't know if this. Let's see. So we want this in the thing. If it equals 0, it continues. And so what we're going to do down here, the way it does that is, if I can click on it, is over here. It's going to do test EAX and jump if equal. So that we want. Let's change this. We'll come here and we will change this to jump not equal. Oops, let's make this jump not equal. And we want to make sure we fill with nops and keep size. Now it shouldn't matter here, but if we were to if we were shrinking something way down, we want to make sure the size stay the same. So that just changed that 1 byte. Looks perfect. So now we can come through here. We got back a value of -1. They don't match. And so we will now make the jump because we changed it. Now we'll come down here and we'll see what happens. And come over here. If we come back, let's see, check to Ghidra, and we can say, if we know like this is the decrypted password, we can rename this function like decrypt. And look, it's calling that same function right here. Still using local 40C and now using another global that it's going to decrypt. So if we step over this, let's see, presumably we think we're going to is it local for, no, maybe this global is going to be what holds the resulting value. Does that get pushed back somewhere? I'm not quite sure. Let's see. So we want to see the global here is, let's follow it in the dump, a bunch of stuff. Let's just step over this and see what happens. And bang, there's the flag right there. Mixed mode for life at FlareOn.com. So we've solved the challenge. I'm going to go ahead and call it here. I thought this was an interesting example. I don't know if it was intended to be debugged this way, but they didn't put anything in place that really prevented us from doing it. And so it kind of feels like a way we cheated a little bit. So thanks for hanging out with me today, and I'll talk to you next time.